All right, tonight we're pleased to have Alex, who most of you know, Alex Woronow, is going to share with us some original research which he's been working on for the last several months. So, Alex, if you're ready, the floor is yours.
Okay, I'll start up. Whoops, we have to do the share screen first. Okay, you should see my startup screen. Does anybody see that?
Looks good.
Okay, let's get on with it then. What I'm going to talk about today is the need for luminous subframes if you're taking RGB images. And I'm not talking about narrowband, just about wide band or RGB images. And probably somewhere along the line, you've been told that collecting luminous subs is important to make your images show more detail. And in the olden days, that was probably true. It doesn't appear to be true anymore in light of our modern technologies. And that's what I think has made these L frames arcane, although the word hasn't reached everybody yet. In fact, as many of you know, I don't really capture most of my images. I buy unprocessed subframes, and you buy them in a batch, and you got RGB and L. And whether you want the L or not, you've got it. And so you pay for it. And it was the fact that over a period of time, I started noticing that I wasn't using the L, and I liked the images I was getting, plenty of detail. And that made me think, why am I paying for the L? And then I thought some more and wondered why anybody was paying for the L. So I started doing a little research on the topic. And the purpose of this research was to answer the questions that follow. Why do we augment RGB with separate L captures? I wanted to determine what role L actually plays in our perceptual detail that we see in an image. Propose alternatives to using L while achieving the same or better detail in our images, and finally to evaluate which alternative approach to the L subs really does the best and is the most approachable in our workflow. This is going to be cover a lot of preliminary information before I get around to actually showing you what I've discovered, but I think it's all necessary and helps us understand the problem and the solution better. So hold on, bear with me. Here's terminology, and I put this up not so much that I want you to be able to memorize all this terminology, but one of the first things I encountered when reading and researching this topic online, and in fact, buying several books.
Are you switching screens, or are you still on the first introductory screen?
Oh, hell, that's too bad. Let me see. I'm not sure what I did wrong then. Nope, I've switched screens several times. Let me see. Stop the share. This is it's not coming up correctly on my view here. Let's see if I have. I can't find my sharing the way I wanted. Okay, I'll just work around this. Let's see here. Share advanced portion of the screen. Share. Okay. You should now see a slide that has a color wheel in the upper right-hand corner, do you?
Yes.
Okay. This will get us there then. Is it a reasonable size? Because sometimes I have trouble with size because I have a wraparound screen. Anyway, so you only missed one slide, and it's no use going back for it. So these are just some of the terms I encountered, and it's a very confusing set of terms. Color, chromatic, chroma, saturation, colorfulness, hue, all these things have overlapping definitions virtually and circular definitions very commonly. So I'm going to try to use the terms appropriately, but if I slip up, it's no surprise because most of us, I don't think, bother with this terminology in detail unless that's our field. And certainly the articles I read have pretty much ignored being rigorous about the terminology. In the lower right here, we see an area which relates to things called color spaces, and most of our programs allow us to go between color spaces either explicitly or implicitly. Like for instance, if you have CIELAB, this is the luminance, the subframes you have are in these coordinates. And here's your RGB coordinates, and these two are connected through this XYZ coordinates. So when you say you're going to put this L into the RGB, you have to convert your RGB to XYZ, XYZ to LAB, add in the L, back to XYZ, and back to RGB. Now the RGB image then has L in it, but it's still an RGB image. And all this goes on behind the scenes, thank goodness. The equations are not always easy to do this, but it's going to be one of the things we will see over again later in this presentation. Okay. So basically, it's a very simple thing. R plus G plus B equals L. And that's comes from the fact that all we're doing in our cameras is counting photons. And if we have three filters, the R, G, and B here from Astronomy filters, and here's the L filter, you can see that if you add up all the photons that are captured through an L, captured through the green, captured through the red, blue, green, and red, then you basically get L. Now, there may be a few gaps in here somewhere. Different filters are different from this. Some have big wider gaps. Some cover closer to the edges of their corresponding L and various other things. But basically, this is true because we're just doing photon counting. And all our filters are doing is parsing the incoming photons into the different colors. And when we take an L, a luminance filter, the broadband L filter here, it doesn't parse those. So it just simply counts photons regardless of their wavelength within that bandwidth. So it just counts 1, 2, 3, 4, 5, the number of photons coming in. So essentially, the L is a poor man's RGB in that the RGB has more information. It has a photon count and the wavelength of those photons, at least an estimate of the wavelength, whereas L only has a photon count. The only advantage of capturing L data is that it provides some of our RGB denoising. And I'll talk about that a little bit more. But that was the original reason why L was captured, is to suppress noise, increase signal to noise ratio, and as such, make faint signals more obvious in our image. And in that sense, they're providing detail, but they aren't providing it. They're subduing the noise. And by that means showing the detail that's already there. Okay, so here's some of the misconceptions that abound about RGB images. And an RGB image only has 3 layers within it. Mathematically, every pixel, there's a value for every pixel in the R layer, the green layer, and the blue layer, 3 separate values. There is no L layer in here. Those people speak as if there is. There isn't. Okay, somehow they persist that there is such a layer. Perhaps it came from the old days of using Photoshop as the only tool really available for doing image processing, or the best one available for doing image processing, where you combine the L with the RGB through a layer, a blending layer. At least I suppose that's what's doing. I don't use Photoshop. I'm just making a guess at why people think there's an L layer. When we capture L into an RGB image, and say we had an RGB pixel that was 200, 10, and 50, that's R, G, and B. And if we add L to that, it might become 240, 12, and 60. But it's still R, G, and B. That's the only information we have kept in our RGB image, even after adding L. Here are some of the things I found on the internet, very quick search, just to see what people were saying. And these first few are quotes. It said that, for instance, for L RGB images, the detail comes from the L channel. These were on cloudy night. It said if you want luminance for the detail, you want luminance for the detail and RGB for the color. And finally, color lacks detail. None of these are true. Even Robert Gendler, way back in 2015, who was operating in Photoshop, said L will provide almost all the detail and contrast in the final L RGB composite. And that's also false. And David Payne, who recently gave us the generalized hyperbolic stretch, has a YouTube that was recorded by the San Jose Club, I believe. And he stated in that video at least twice that we add L to our images for detail. All of that is false. If you think of a CFA chip, every photon is captured through an RG or B filter. None goes through an L filter, and yet there's detail in the resulting image. And how can that be if any of these are above or true? It's because they're not true, of course. So what really happens, whoops, and this isn't going to work. That's strange. I'm going to skip this slide because of that. I have plenty of slides. So here's another example. If we take a gray image and we add it, this is our luminance effectively, and we add it to this image, which has gray, it has R, which is purely R, G, which is purely G, and blue, which is purely the blue. And if we just add this to this, this is what we get. And so now, if you look at these values, they've all been distorted. The colors are not maintained correctly. This is what L does to our image, adding to our image. And it does other things, like I was saying. For one thing, adding a lot of L subs together suppresses noise. And so that would happen too, but it also has this detrimental effect of changing our colors, particularly color saturation. As I said before, we use a color, we go through XYZ, RGB to XYZ to LAB, for instance, in order to add the L to the RGB. And when you do that in PixInsight, I used the L RGB combine tool. I think there's another one you can use. You just put the L frame's name in here, and then you drop it onto your RGB film and it modifies that frame appropriately. There's also lightness and saturation controls on this. And you think, well, why would I want those? Well, the answer is from the last slide. If we do that look at that last slide and remember what it looked like, we're changing the saturation and the lightness of the slide of the color. Changing the lightness and saturation of the RGB frame And this would allow us to counteract that to some degree. In fact, we can't counteract it entirely by these two sliders, but we can come close. And this is kind of what we're doing. This is showing in a different color space. It's in the HSL color space. If we had a color down here and we added luminance to it, we move upward and inward in this diagram. Luminance is the vertical axis in here. And these colors are what's called opposing colors. So red is opposed to green and yellow is opposed to blue. Interestingly, apparently this is the color system our eyes use, despite the fact that we only have RGB cones in our eye. The way our brain interprets those RGB cones is in this competitive system of yellow versus blue and green versus red. So whatever that's worth, things I learned on the way, I guess. So why were L subs ever captured? The only benefit of collecting abundant or any L data and then substituting it into an RGB filter and image was to suppress luminance noise in the color image with that more rapidly and easily obtained L data. We do that only to improve the signal to noise ratio in the RGB image, and it does that. And that means we reveal more of the signal at the lower light levels, and that appears then to have added detail when all it's done is reveal detail that was already there. And the question now is, the question that crossed my mind was, so is that was true in the old days when we didn't have the tools that we have today. Is it still true today? And the answer is simply no. And we have many modern noise reduction techniques. We have new noise suppressing stacking technologies. There are 8 different alternatives offered in PI for reducing noise during stacking, different stacking methods. I mean, there's well, I'm not going to go through the list, but there are 8 different ones, for instance. There's AI noise reduction in technology, and noise exterminator, for instance, and topaz denoise, and deep signal to noise ratio are 3 of them that come to mind. And to a lesser degree, there's other noise reducing techniques that are available now in our image processing tools like wavelets, array denoise, etc. Plus, for many of us, a lower read noise in the CMOS and recent improvements in CCD sensor noise have helped reduce the noise in our image. And if we reduce that noise by these techniques, it's just like reducing it by adding more L. We improve the signal to noise ratio and reveal more signal, more differences, more detail near the signal to noise ratio or near the noise limit. So compared to collecting large banks of luminance image, which takes a lot of telescope time and processing can take a lot of computer time, these new technologies remove the noise just as effectively. They increase the signal noise range at least as good as well, and do so in fact with more quickly and with less effort. And comparing the detail contact of what I call L extracted, that is L pulled out of an RGB data, out of an RGB image. You can call a function in PixInsight to give you the L that is hidden in that RGB image, again, by going through the XYZ and back to LAB and coming back and getting the L then. So what I'm going to do is compare this thing L extracted with L captured, and in 2 images extracted for 1 image, I'm sorry, with 2 different ways of getting L, and subject both those to AI denoise and to demonstrate the fact that you don't need L anymore. Actually, some people already know that you don't need L, and here are a couple more quotes from the literature. And it's, I won't read them to you. I'll give you a second here to read them while I think about the next slide. But people do know that you don't need L. Okay, the principal question then is, does AI noise reduction do as well or better than capturing separate Ls? And so as I said, I'm going to compare this L extracted from an RGB image with L captured separately for the same equipment, for the same target, and see if there's any difference between these L values. If there's no L difference between these L values, then substituting the L capture for the L extracted gains nothing. And the amount of time, I'll look also when L extracted more or less equals L captured, and in other cases where they've captured far more time than in L than they did in RGB. So the RGB extracted is a small compared, so based on smaller sample number and smaller acquisition time than L captured. I use quantitative and qualitative tools to do this. And if no significant difference is found between the L extracted and the L captured images, then there's proof that the separately captured luminosity data is not providing any additional detail. Okay. And now I guess we should discuss what is detail. And I really couldn't even find a good definition of what is image detail on the internet. I think we all have a feeling for what it is. And it's something that's at the very fine scales and perhaps at low contrasts, and something that image processing strives to reveal. But what controls how much detail we actually end up with in our final image, our final RGB image? And one of the things is, in fact, that we take enough images. We have to have enough images, even in the RGB channels, to suppress noise in those channels, at least some, and to bring out subtle differences in hues and tones within those colors. We're limited by our equipment, and we all know about things like DAW is the limit, and we can all calculate the resolution of 1 pixel, for instance. And so there's some equipment limitation on what level of detail an image can possess. We also are limited by the sky and seeing limitations, by the display limitations. We display our images by either printing them or bringing them up on a screen. In either case, our displays have limited color spaces. Most of them are sRGB, which is a very small color space relative to others. We have limited bit depth. 8 bits usually is common. Occasionally we find 10. Unfortunately, some printers we find less than 8. And then there's visual perception limitations. The number, size, and distribution of cones and rods in our eyes limited, and the way our brains process that data that those cones and rods capture is limited, and it limits our perception of detail in images. And these are compounded, of course, by the limited color spaces we work in. For instance, if we, and I have maybe for another talk at another time, an image, here's what something you can do. You can take one of your images, RGB images, and extract the L, then change the L to the red channel of a colored image, and just have a red channel. All the L data is now red. Then make all the L data blue and all the L data green, and then blink the 3 and see which one you think has the most color. The most detail. And you're going to find that the green image has far more detail than the red, and appears to, and the blue lies between them, the red and the green in detail content. In fact, they have exactly the same detail. It's our eyes and our brain are not interpreting the detail in the red as effectively as they are in the green and blue, particularly the green. Anyway, another possible limiting thing for how much detail we have is our our processing capability. If you if you're a novice image processor and don't have a lot of experience at bringing out detail, chances are you don't bring it out, in which case that limits what you're able to see on a screen or in print. And in fact, in reality, many of these things can work together to limit what our image actually has. So there we are. Theoretical limits on image resolution probably don't mean much. It's probably more our processing capability and probably our equipment for displaying and even for processing the images. Okay, so here's how we're going to compare image detail. Those two great images I talked about, the L extracted and the L captured. These images are processed in an identical manner in the following examples. The images were calibrated and stacked using WBPP in PixInsight. They were stretched using the screen transfer function plus histogram transfer. That is the simplest way that I could think of that probably doesn't introduce any extraneous processing that's hidden behind some of the other stretching algorithms, or perhaps hidden behind some of the other stretching algorithms. Sometimes I adjusted the black point to remove the totally black pixels from the image. I never tried to actually truncate any of the pixels that had a level above 0. I removed the stars, usually, not in all cases as you'll see, and used noise removal tool. I used noise exterminator. The images were enhanced minimally. Sometimes I did a bit more, as I'll describe below, but usually just enough to show some detail so that it's visible, rather than just being a blob in the case of a nebula. And then the image underwent something called histogram matching before being compared. And histogram matching I'll go into a little bit more later. It's not a tool in PixInsight. I wrote Python code to make a histogram matching algorithm. And anything I write, whether it's in Python or PixInsight script or Pixel Math, I'm 100% willing to share at any point with anybody who asks. So if you see something you like and want it, just let me know. Okay, image comparisons. Once I've done these things to the L extracted and the L captured, I had 3 ways of comparing them. I blinked the 2 images. If the blinking shows the images are perceptually the same, then the L captured and the L that was already in the RGB image, hidden in the RGB image, are identical, and we don't need to add that L. I took a difference of the 2 images, the L captured minus the L extracted, and added 0.5 to shift it to the center of the range 0 to 1, so we can observe it. And again, if this thing ends up being a flat image with a constant value, then L extracted equals L captured. And finally, I measured a multi-scale perceptual detail index using a code based on a paper by Wang et al. And I'll talk very briefly about that. It's really very complicated. And that too is in a Python script, Python program I wrote. So here's what I did. I made an RGB image, and L extracted is simply equal to the sum of this RG and B. And you can either do this by adding up every individual sub before stacking them, or you can stack the images and take our RGB. Oh, I'm sorry, the stacked images. I did this with stacked images. There we go. And this has an equivalent exposure time of R plus G plus B over 3. So that's because if you had 20 minutes of R and 20 minutes of G and 20 minutes of B, then you'd have an average, you'd have 20 minutes of total exposure time of the sum of those two, of three. In comparison to an L, it would be matched by 20 minutes of L. Then I did the histogram matching and a quantitative analysis using a program whose abbreviation, believe it or not, is MSSSIM. This is short for Multi-Scale Similarity Index Measure. There'll be a test later. Okay, histogram matching. It was the first step I needed to do, or one of the early steps I needed to do. It takes a cumulative histogram of one of the images and relocates the pixel intensities in the second image to match those in the first image as closely as possible. And it does this by not rearranging the order of the brightness of any of the pixels. It's all done, not sure what the right mathematical word for it is, but it's consistent. It's done on a cumulative curve. So the values of pixels are shift in toto to a new position. They aren't some made brighter and some made dimmer. They're all either made brighter or dimmer as needed. It's basically a complex curve transform with a monotonically increasing curve. If you're looking at it in fixed insight curve transforms or something like that. It's never a perfect process because of histogram binning. His pixels are binned. If you have 8-bit pixels, then the 8-bit binning is limiting you. If you have 16, then the 16-bit resolution or binning is what limits you. Once done, images A and B can be compared either visually or statistically, and they can be blinked, and it means something because they now have the same distribution of brightnesses as each other, or at least close to it, as close as you can get. Here's an example of my histogram matching program and what it did. Here's a target image. We want to mark that target image to the reference image. So here's the target histogram. And here's the reference histogram. And after taking the target, saying match it to the reference, here's what histogram the target looks like once it's been matched. So it's done a pretty good job of taking this and converting it to that. All the peaks are still in the same places, or the same peaks. See, this big peak is in both of them, the target and the reference, and it's preserved here. B, A, the pedestal is shifted a bit, but it's still down here. B, D, and E can all be found in all three images. So this is the effect of histogram matching. Now I could take this image with this histogram, overlay it on this image and blink them, and they should look pretty similar. If I blink this one with this one, even though they are similar, the stretch is different and they're not going to look similar. Okay, then for this MSSIM, I compared the structural content. It compares the structural content of the two images. It grades structural perceptuality or something like that. Differences on a scale of 0 to 1, where something that is 0, a pixel that has 0 is unmatched, and a pixel that is in the two images, value that, let me start again. The pixel value from this perceptual match, if it comes out to be 0, then the pixel is unmatched in the two images. If it's 1, there's a perfect match in the two images. My implementation slices the image up in this pyramidal way and evaluates the resolution at the different levels of these ever increasing. This is the full resolution. This is half resolution, quarter resolution, eighth resolution, and I go down to 16th resolution. But it looks at the resolution in each of these different levels and compares them and gets a index for the entire image for each of those levels. The method doesn't tell you exactly what the match or what the mismatch is, but it can tell you where that mismatch is in the image, where the mismatches are in the image. And it then quantifies the mismatch in the entire image as well as it mismatch pixel by pixel. I'm going to look at bright nebulae, at least one, a galaxy, and one dark nebula. These are post-processed in Pixel Insight, as I said, and some of them a little bit more in Studio 2. So here's the first one. Let's see if that blinks for me. Oh, come on. Don't do that. That's the fits. What are we going to do now? Okay, now screw it even worse. Now there's back. Oh, crap. Let's see how I can do this. It was blinking for me earlier today. Okay, let's start up here in the corner anyway. And here's a similarity scale at each level. Level 0 is the full resolution of the images. And it has, if you want, 91% structural perceptual match between the two images. And as you go down to lower and lower resolutions levels in the image, it goes to a better perceptual resolution. Let me try something here.
We know Murphy's Law works.
Yeah. Slideshow. Yeah.
Alex, try taking it out of presentation mode.
Okay, you mean stop yeah, out of presentation? I think it is out of presentation because I've got this whole stuff here on the side. I've just fenced off this part. I'm actually wanted to go into presentation mode, but it won't go. Yeah, it's not showing. Yeah, but it doesn't do anything. See, it's not. There's not here anywhere. It's because of this over here, I think. Okay, I think I've got it. I can get there. Okay. I'm going to go to a different screen here, where I think I have it. Yeah, I have it. Back. How do I go back now? Does anybody know how you click a slideshow to go back? Escape. No, that didn't work. Okay, now it's working over here again. Okay, we'll go back here. And sorry for this. But whoever said get out and get back in was right. That was, in fact, what was happening is it was hung on a golly, where's the bottom of this thing? I have another problem. Okay. Yeah. Okay. Do you see that now? And it should be a blinking slide. Anyone out there?
Yes.
Okay. So now this is the comparison of the extracted and the captured slide. And after histogram matching, down here you can see which one you're looking at. So that's the L extracted from the RGB, and that's the L captured separately. And there was 4 hours of L captured, and the extracted L is equivalent of 1.3 hours of exposure time. And I'd say those two are pretty much the same. So that if you dropped this L into place of this L, I don't think you would get any more detail. And these scores up here imply that this is considered a very strong match between those two slides. Okay, here's a case where I enhanced that previous image quite a bit in Topaz, and then blinked it, histogram matched and blinked it. And once again, to me, the detail level in those two is not easily discerned. Any difference is not easily discerned. Here's what it can do. This program can do. This is what's called, this whitish one here, not that one, this one is called a similarity map. And anything white is a perfect match, and black is a perfect non-match. And first we see gray levels in this image. The boxes in the image are the areas where the mismatch occurs. And one thing you'll notice is that most of the mismatching is occurring in darker areas of the image. And that's apparently a flaw in the algorithm, not in the technique of this image matching appraisal method, is that it's more sensitive to differences in dark areas. So it overestimates the difference in areas that are in fact very similar to our eye. So here where the nebula is, there are very few mismatched areas. And those that are there are very fine. This is a galaxy, obviously, NGC 300, and this is blinking the difference between, is this equation. I took the L captured, subtracted L extracted, and added a half, and most of the image is pretty flat, saying that before and after the L captured and the L extracted are about 0, and the image is about 0.5 everywhere. And here we only had 1.4 equivalent hours of RGB yielding the L extracted versus 5 hours of extra L. That 5 hours was wasted. We have the same image regardless of whether, if we just not captured that at all. This is a blinked
Extracted, right?
Is that the same one again?
No, you're just seeing the difference in L captured.
Yeah. Yeah, that's it. The difference in L captured. So you can see where there's less difference out here, some very slight differences in the galaxy. Okay, and here's the similarity map for that. And once again, the similarity map is almost perfectly matched. That is bright equal 1 areas in the area of the galaxy. And out here, we're in the black skies, there's more mismatch. And that's a result of the fact that this algorithm is not terribly reliable at low light levels. Horsehead Nebula, for a dark nebula. Now I have, whoops. Now I have 4 hours equivalent of L extracted. That is 4 hours of R, 4 hours of G, and 4 hours of B, and 14 hours of L. And so here's 4 hours of one and 14 hours of the other being blinked. Look at the similarity score. Try it. Look at the similarity score here, 0.99. So that 14 hours of L captured was a total waste of 14 hours of telescope time. This is a similarity map for the horse head. You see, there's some areas here right along the edge where there isn't a real good match. And this area down here where there was a star patched into the starless image is bad. But overall, this is the histogram of the mismatched values where one is perfect match. And you can see the histogram is all up here. Pretty good. And like I say, none of these methods are absolutely perfect in matching the histogram anyway. So there's still going to be some introduced error from histogram matching failure. Okay, my conclusion is that augmenting an RGB image with separately captured luminosity subs does not enhance the detail of the RGB image if modern denoising techniques are used. But there's more research to be done. Anyway, future research, things I want to do, spins off from this are comparing 2x2 RGB with 1x1 L captured and seeing if you're getting full access to image detail if you opt for 2x2 RGB or not. I don't know the answer at this point. How much exposure time is enough? That involves us taking a number of L slides, subs, making an image out of them, taking maybe twice that many, making an image out of them, and so on, and then comparing them step by step and seeing when you don't get any improvement in image detail. And at that level, you've captured all the L that your seeing conditions, your scope, your processing capability, your techniques, this, that, and the other thing have peaked. And that's as far as you ever need to go. Yeah, it's true. If the seeing gets better one night, you may have to creep up a little bit, or maybe allowed to creep up a little bit, but that's about it. And then I want to do a little demo on how color degrades our ability to see the detail. And I've already kind of previewed that one for you. So I actually have written up an article about this, which I will make access, give a link to on our website. It has all of these illustrations and much more discussion. I don't know why I do that. I guess it's left over from my research days at the university. I have to write things up. Also, as I get older, I forget things quicker. It's nice to have them written down. So, any questions, folks? I'd be happy to try to answer them.
First question, what kind of a camera did you use?
The cameras were different. They were taken by different scopes and different cameras. So they were all high-end scopes. They were all taken CBK 17s at various different locations with different cameras. But high-end cameras. These are people whose images acquired through Deep Sky West and through iTelescope.
Would this apply to someone who's just using a OSC type camera like a ZW0553 MC?
Yeah, one-shot color, it absolutely applies. It means that, in the sense that it means that you're not missing out on anything. You're getting all the detail, given your resolution, given the fact that these pixels, are grouped together to make one pixel in the processing, the RGB pixels. But you're getting just as much quality from detail in your images as anyone using a grayscale camera is getting.
Alex, in one of your early slides, you showed adding a grayscale image to an RGB appears to have a significant color shift.
Yeah.
Of the RGB. Is that magnified? Well, in your graphic there, is that effect magnified? Because I know a lot of people add L to RGB, and I would think if it caused significant color shifts, that would be well noted, and there would be fixes for that and so forth. Is that Is that,
Well, it may be somewhat exaggerated here. I'm not sure what that means, but I've certainly observed it in my image, in my images. In fact, I have one image I didn't show. I decided to show this one instead, where I took a RGB image and added L to it, and things that were a bright orangish red shifted to a much paler diluted orange red color.
Hmm.
I mean, this is an easy one to try in PixInsight. It's pretty easy to make up an image of any one color and just add a gray image to it. And I think you'll get the same results. And what's happening is the saturation is changing. Saturation in an image is defined by the amount of white that you have. So it's the amount of if you took a pure red image here, this has 0 white, RNG or 0. This one has equal amount, has 50% white added to the RGB, and that's from adding this 50% gray. And so this is how, I'm sorry, that was the wrong one. This red here has, okay, about 38% white added to the red. And as such, it dilutes it down to this particular saturation. It's largely the saturation that's changing, not so much an actual color shift.
the hue, yeah. So
Yeah.
are people just tweaking up the saturation a little
Yeah.
bit to compensate? Is that all that's going on?
I think that's what's going on, but in fact, you never recover that original color because the hue does shift a little bit in the process. And so at least I haven't found a way to diddle with it to get it back. I tried, and I tried twice. Didn't give it a real hearty effort, but I gave it an effort, and I couldn't get back by just changing the brightness and the saturation. Maybe somebody else can. It's fine if you can, but then it kind of makes you wonder why you're adding it in the first place if you get back to the original image. I don't know. It's a complicated thing. A lot of it seems very circular. I don't know. At least it was for me. Confusion comes easy when you're 77 years old, but this one certainly did it.
Okay, thanks.
Sure.
But Alex, will you go back even maybe one more slide? Show the spectral response curve again, will you?
Spectral response curve.
You know, the 3 overlapping, the RGB response.
That one there?
Yeah. So in a similar vein, though, I mean, you have another kind of problem here. You have color confusion here, right? Because if you look at, say, 600 nanometers, you've got, some of that is showing up in the green channel, some of it is showing up in the red channel, and at 500, you've got green and blue. And so in a similar way that adding luminance causes problems for color, you've got color confusion. And I'm a big fan of OSC, okay? So don't get me wrong, I love the OSC, but this is one thing that's always bugged me a little bit about OSC is that
I think
some of this is showing is confusing.
I don't think, there's not a problem here if you look at it as counting photons. You only have one.
No, from a detail perspective, I agree with you, but I don't know that the whole conversation is just about the detail.
This is
It's about maybe fidelity of the colors as well.
Yeah, okay. That's
Because if you combine, if you
You're
took
right,
the
you're right.
old school,
No, I think you're absolutely right about when you make that into an RGB image, you may not have the correct RGB, but you have the correct number of photons. And
agree.
yeah, because a photon coming in here, when you have a red filter in or a green filter, you're going to capture it. It's true.
No, but imagine old school.
You're only going to capture it with a 50% efficiency, but it's 50% in each one. And
Right.
so that brings you back up to here.
But you can imagine the old school where they're talking about, okay, maybe you're doing narrow band. You only want just enough color to get, correct colors, and you don't need a huge amount of color, but you want, if you just took a luminance and then added just enough color in a narrow band to get the colors proper, then potentially the argument changes a little bit, where, you've got some color confusion, even though you've got the detail. And in the old school mechanism, where you took the luminance and then added just enough color to get the fidelity right, you would get the best of both worlds. You'd have the detail on the luminance.
You still have the color confusion if you're using these filters.
No, I'm talking about narrowband.
Oh, narrowband. Yeah, if you're using narrowband, I didn't address narrowband at all. If you're using narrowband, there certainly is the possibility to, like you say, to map those into RGB color and then to use luminance for something else. But I think the problem we have is thinking that, say, a photon at this wavelength is captured by L. The fact of the matter is that the photons captured here are divided up. I guess this is the slide I skipped because it wasn't very good. But a photon coming in here is photons, say at 100 photons coming into this part. And somebody says, well, that's filling in information at a different wavelength. Well, those 100 photons, 6% of them go into the blue, 72% go into green, and 22% go into red, even though they all came in the far red. So it's not helping you at all in terms of filling in blank spots between your colors. You're dealing with photons again. And
No, wait a minute, you lost me.
This
Something didn't ring true
okay,
there. You're
back.
saying,
let me go back. Let's just say,
go back to 650 nanometers or maybe 690 nanometers and tell me why it's going into the
I want to go
green.
here because it's easier to explain. So
Yeah.
if you're up here around 680, and a photon comes in while you're taking this L image, 100 photons come in here. Where do those 100 photons go when you mix them with your RGB image? They go through a part in PixInsight called the RGB working space. And the RGB working space tells it how to allocate luminance data into the RG and B levels. It says
You're talking about the mixing proportions.
mixing proportions. So 6% of those photons that come into L, regardless of where they come into L, 6% are going to go into blue, 72 into green, and 22 into red. And that doesn't matter what you do. And since we have so few green objects, we're wasting photons galore if we use this method.
Why are those photons recorded at all? The filter should be blocking them.
No, the filters don't. If the only filter you have is L, I'm talking about. If you have only the L filter, then those other filters aren't in the system. So L just lets everything within this area here through. This is if you have just the R and no other filters, just the green, just the blue. And this is adjustable in PixInsight. I don't know whether it's adjustable in any other programs. I've never seen it. But in PixInsight, in fact, Juan suggests that maybe it would be better to make these all 33%, 1/3, or even better to make them make this maybe 15%. This may be maybe 40%, and the rest of it, most of it going into R. So you can adjust this, and I always adjust it to even 33, 33, 33. If you leave it like this, then all your filter is doing is pumping up the green, and then you do a color calibration, and it just wipes that back out, or SCNR, or whatever you do. And it wipes.
But again, you're still stuck with color confusion, right? So I'd say that the quality of the image is in two pieces. One is the detail and one is the color fidelity. And in both of these mechanisms, color fidelity is suffering as a result of the games that are being played with luminance.
Yeah, I only addressed the detail here. I didn't address the element. You're right. It appears to me that certainly there's issues with that. And another brand of filter, and I don't remember which one it was, the green is shifted way over here, so the peaks are almost the same. And this one overlaps all but about, I don't know what, a little bit. Maybe it's instead of this one coming down at 400 and green coming down over here, green comes down at 470. I'm 370. I'm sorry, 425 or something like that. And so that overlap is real heavy. And what you're mapping into green is really shifting quite a bit into the blue. So yeah, there's issues like that. Supposedly color calibrations rectify at least some of that problem, but I haven't analyzed that one yet. I got a task for you, Doug. Are you taking homework? Are you taking homework?
No, I'm not taking any over. I'm just frustrated, that's all, yeah.
Well, if there's nothing else, I'll shut this down and give the screen back to the group.
People who take just RGB images, is everybody extracting a luminance and processing it separately and reintegrating with the RGB?
No, most people just leave it alone.
I don't. I'm just wondering if I'm missing something. I seem to
No.
get a reasonable amount of detail on just the RGB.
I went through my first phase of ignorance was just taking the L and substituting it into the RGB image. Very often the amount of L was equal to the amount of equivalent L already in the image. So that's really a dumb thing to do. Then I went to the next phase of making what's called super L, that is adding the RGB and L together. And that one makes a more effective L, and then putting that in the image. Then I got tired of just processing all that L and just started doing RGB and throwing out the L. And I noticed that it didn't change my happiness with the images I was getting, and that led to this piece of research.
Let me ask the question another way. I have an RGB image.
I can't hear you.
And I extract the luminance and I process it as well I can to bring out details and clarity and so forth. Alternatively, I just do the same thing to the RGB only image. Obviously, I put the two back together if I've extracted the luminance. Is that a waste of time?
Yes. The thing about it is, and let me start with one part of that. When you extract the L, now you have an L, and now you have an RGB image, but the RGB image that you have is exactly the one you started with. So when you're processing that separately from the L, you're effectively processing the image you started with before you extracted the L. So if you can make that one happy in terms of detail to your contentment, then there's nothing left in the L. It's true that no, it's not true. I haven't ventured into the idea of processing both those separately and putting them back together. But the L just doesn't. If the point of it is you can get the same detail in the RGB. So extracting the L and processing separately and putting it back in, that can't gain anything. If you do.
Well, hold on. There might be a slight caveat there. If you think about a spot diagram for a telescope and you think about how red and blue are sort of ballooning, here, the spot sizes are bigger and they're more spread, vertically. If you compare it to the green, for instance, and then you take a synthetic luminance, okay, you extract the luminance out and process that part of the image, you're probably processing more of the green and less of the blue and red. So it could be that the sharpness of a synthetic luminance might actually be a little bit better than the RGB combined, which is going to have that blooming of blue and red on the spot diagram, right? So you get those color halos are going to expand, and if you can get away without processing some of that area of the image and stick to the green, you might be a little better off. We're brainstorming here, but again, there might be a subtlety there.
There's not much green in the image to begin with, but in any case, I'm not sure I totally follow you, but I now take when I make my stacks of RG and B, I go into the blur exterminator and I measure the full width half max of the R image, and then I correct it an amount that matches it to the green. That is, I effectively change, what's the word, deconvolute the image so that it has the same spot size as the green image's spot size. Then I do the same thing separately to the red and move its spot size to the red spot size. Now, I don't expect anybody else to go through this shenanigans, but I do that. So that's how I take care of differences in spot sizes.
No, I can see that for sure. If you're running Blur Exterminator, you're going to be neutralizing some of those differences for sure.
There's other things floating around out there that people are unaware of. There's aliasing in all of our images, and it can be quite a bit. And there's a very simple procedure called Nyquist reconstruction that I use to get rid of all the aliasing before I start processing anything. And it's funny, I've never seen anybody in astrophysics and astro imaging mention it before. And in Blur Exterminator, in the write-up of it, Russ mentions the procedure. He doesn't call it Nyquist reconstruction, but he outlines the steps that are used in Nyquist reconstruction and says, yes, they are useful. So I thought that was some validation of something I've been doing for a while. I could also send anybody who's interested in that the script. It's not a script, it's just a Pix Insight, Pixel math. But I don't know how much effect it actually has on my images. It's hard to assess, but I know that signal processors use Nyquist reconstruction all the time in audio and video signals.
And just to cover one point again, so as we're talking about this is really talking about with a monochrome camera, because it would be completely different with a one-shot camera. Is that correct?
In one-shot camera, you don't collect L, and you've got, the thing about it is you have all the information available to you that would be obtained in a one-shot color camera with the same effective pixel resolution. You have the identical.
Right, and because of the Bayer matrix, you've got a different profile on that as well.
Yeah, but outside of that, it's the same thing.
So I have a quick question. Is for somebody who didn't know how to spell WBPP until last week. What's the advantage of using a monochrome camera versus an OSC camera?
More expensive filters.
Wider wavelengths. Because you really can't capture narrowband with a one-shot camera.
Oh, even with a filter? Like an IDAS filter?
Well, you have that filter, but then again, the Bayer matrix also has is in there. It's going to manipulate it as well.
I mean, in theory, if you have a red hydrogen line, it should be recorded in the red part of the Bayer matrix. But I don't know. I don't really know that's it. It sounds good in theory. I don't know what happens in practice.
Yeah, this question has been debated, ad nauseum on all of the different forums. If you go out and you look at and ask that question, or do a Google search for that question, you'll find that wars have been started and never finished on this very topic. So probably we're not going to answer that question here tonight. However, color confusion definitely plays a factor there, right? That chart that we looked at where the colors are overlapping, this is one place that you cannot succeed with a one-shot color where you could potentially succeed with the monochrome. Yeah, and there's no debating that. The rest of the story about how much signal you gather and how much integration time you need and whether one's better than the other, that has been fought about since OSC came out.
But OSC is a whole lot easier.
Whole lot easier. Yeah, magnitudes of difference there.
Well, I'm having a lot of fun with it. I've only been doing it for a couple of months, and unfortunately, the weather hasn't cooperated. But I'm only an eighth through the rabbit hole at this point, so I'll probably end up getting a mono camera down the line. But right now, I'm just going through the basics. It's a ton of fun, though.
It is, and mono costs a whole lot more because you got to buy all the filters too.
Right, and the filter wheel. And then you really can't do a hyperstar with it, I would think, because then, unless you constantly switch out the filters each time in the filter drawer, I guess you could do that.
Yeah, you can, but it's a pain in the neck. It
Yeah.
just takes forever because
Right.
you lose a lot of sleep with if you have a hyperstar and you try to do mono because you have to get up to change the filter constantly.
Right.
Alan knows because I've seen the hole in his dew shield where he sticks his hand in to put the new filter in.
Yeah.
And the flats are hard because you never know what's going to happen.
Yeah, and plus it just takes a lot longer if you're doing mono, because I'm doing mono now, and gone are the days of doing 2 or 3 objects in an evening, like you could do with OSC. With mono, you're going to do, let's say, 4 hours of R and 4 hours of G and 4 hours of B, and whereas you could do with an OSC, you could do that in 4 hours. So Alex, actually, I do have a question. If we agree for now that there's no additional detail gotten from the L, there's a lot of brightness that you get from the L, if that's I'm sure that's the incorrect term, but if I'm shooting a faint image and I do, let's say, 2 hours of R, 2 hours of G, and 2 hours of B, there's some L in that R, G, and B, right? If I do 2 hours of L, aren't I getting a lot more L for my money than doing
No.
another
If
6
you have 2
hours?
hours of R, 2 hours of G, and 2 hours of B, that's 6 hours, and divided by, it's just each cover about a third of the spectrum that L does.
Uh-huh.
So that's 6 hours divided by 3 is 2. And so it's
So that's the same as just doing 2
same.
more hours of L?
yeah.
Well, to be totally fair, go back to that chart showing the spectrum analysis, right? The spectral response, and you see that those have peaks on them, and the L filter may have a higher peak than the R, the G, and the B. And so as a result, there could be some truth to what you're saying, Alan, that you might get a little bit more, but
It's
it's in the gap. Yeah.
If you looked at those filters, the difference between that little gap there is 1 or 2%. And so you get 1 or 2% more photons with the L, and lose the information of what color those photons were.
Yeah, but so then aren't I getting, let's assume the peaks are the same. Am I getting the same amount of L from 2 hours of L as I am from 6 hours RG and B?
It would depend on exactly what your RGB filter band passes are, but the answer is, from a image processor's point of view, the answer is yes. You're not going to notice the difference.
I'm not going to notice the difference, but can I not pick up another 6 hours worth of L in 2 hours with an L filter?
Yeah, but what are you going to do with it? It's going to be spread, and 76% of it is going to go into the green channel. And what are you going to do with that? You're going to rake it out of there using some green noise suppression like SNGR or SNR for.
Look, I'm trying to justify the money I spent on my L filter.
But it's an arbitrary mix. I mean, back to our color fidelity, right? I mean, you can choose to blend in different color, and but either way, it's not a precise answer, right? You're gaming, and either way you play the game, you're not getting color fidelity. The only way to get the pure color fidelity would be to use those narrow band filters.
Yeah, I mean, I thought that's what SPCC is doing for me. It's giving me the correct colors.
I think it's doing a proper white balance, and it is affecting your color calibration, but it's not perfect. You're still getting some of those green photons are going in the red channel, and some of those blue photons are going into the green channel, and vice versa, right?
Yeah, the problem is there is no green photon or red photon. There's a continuous spectrum, and the division between red and green and blue is arbitrary. Where we choose to draw that bound is an arbitrary call, because how red does it have to be before it's no longer green? I mean,
Yeah, I think maybe I screwed that up by talking about color. I'm talking about wavelengths, right? If you just look at nanometers, some of those photons at particular nanometers are coming in the wrong color filter. They're coming through the wrong channel.
There's no wrong filter because we don't know where the filter, a green filter covers.
No, but it's arbitrarily laid down.
Yeah,
It's laid down by the Bayer matrix, right?
Yeah.
So it is coming through, and it's
Yeah.
going to show up as a color.
I totally agree. The same photon a wavelength can be recorded in more than one place. Yeah.
Well, do they make what amounts to narrowband RGB filters, so there wouldn't be this overlap between the three channels, and yet so they'd be wide enough to be reasonably efficient, but not overlap one another. And then you would just take longer exposures, I guess, through each one to get the flux you need, and then you wouldn't have this problem of color fidelity issue.
The problem, I don't know of any that are available for amateurs, but the thing about it is if you say you shrunk them down so there were in fact gaps between the red and the green and the green and the blue, then what happens to those photons that would have been in the gap?
Well, I don't know, but what's the difference? Because
I'm not sure
you're getting pure colors. You're getting pure RG and B. If that's the point of what you're trying to do, and avoid the overlap.
I think the problems are many, and another problem that factors into the same thing is, from rather extensive reading on this, it's apparent that a large number of people, if not everyone, sees colors somewhat differently, has different sensitivities to the different colors, different wavelengths.
Yeah, it's biological.
Color fidelity to one person isn't color fidelity to another person, I guess. I don't know.
Well,
it's in way our brains interpret wavelengths through our sensor to the eye. It's really quite complex and still a matter of a lot of research.
There is an answer to Tom's question, though. There are, I wouldn't call them wide band, right? I would call them wider than narrow, right? I mean, you think about your standard 3 or 6 millimeter or 3 or 6 nanometer filters, those are clearly narrow band. You can buy like a tri-band filter that is wider than that. I think maybe as much as 15 to 20 nanometers, so they're not great for moonlight, because moonlight will sneak in there. But you can buy a wider filter. Yeah.
Another interesting.
I think that was the whole point. I was just saying, since this seems to be a troublesome issue for a lot of folks, I would just think that, again, going the narrow, let's call it not narrow band, but narrower band RGB filters would you'd at least avoid some of these issues. And the data you collect, is totally attributable to whatever wavelength, whatever bandpass those filters are. You can mix and match them any way you want post-processing, but what you're starting with, at least, is not pre-mixed as they are, as your spectrum chart showed there. So
I think part of the issue with filters is going to be the cost to actually produce a filter that would properly separate each of the color wavelengths and leave that tiny little bit of gap between them. I don't know that we could ever even afford such filters.
Well, I mean just regular, individual filters, not a single filter that does this. You would just have essentially narrow band filters like you have now for sulfur and oxygen. Oxygen 3, only just have them centered on the wavelengths assignable to RG and B.
Basically, though, all these nebula and things we take pictures of are emitting in a very few wavelengths that are dominant. So even if we have a broadband our filter. Most of what it's recording, when we look at something like the image behind me, most of what it's recording is hydrogen alpha. There's not a whole lot of other radiation compared to the hydrogen alpha coming in there. And same thing with the blue and the green. They're looking at things like the oxygen, and red, again, sulfur's in the red, but there's a continuum spectrum behind that. And that continuum is really not that interesting. That's why we went to professionals and amateurs go to narrowband filters, is because that continuum is really messes up the detail, messes up the importance of the emission lines themselves. And there's been efforts, more than one, and I've participated in trying to separate the continuum spectrum from the narrowband.
So does it make more sense then to simply select what filters you want, whether it's sulfur, oxygen, or hydrogen alpha, take your images through those, and that level of detail that appears in those filters, which is pretty high, that's what you work with. You can mix that or keep them separated however you like, but you avoid all these issues of overlaps and color mixing and matching and stuff, trying to deconvolve all this color stuff after the fact.
I have a script that you might be interested in. It takes if you have RGB and a narrowband image or two of either H or HSO, it separates the emission line part from the continuum approximately. It's not the equations for doing that are not oversampled, whatever the right word is, overdetermined, but it will give you just the emission lines, and then it will map those emission lines into approximations to true color. So now, and then it will make an image out of them. So now you have a true color image that was just from the emission lines and not from the background. And that there's no mixing, it's just what yours.
Yeah, that sounds like a good approach.
Yeah, again, I have a script, and if anybody wants it, just let me know.
Okay, thank you.
It's gonna, with some of the people with a lot of experience here, I just went on the Chroma filters website, and it seems like there's a lot less overlap. And I did purchase Chroma filters. I'm just kind of waiting for the weather to use my new camera and stuff like that, but there is less overlap. I don't know if people who are experienced with that, if they looked at that, they would say, yes, there's less overlap.
Who makes those? Chroma, you say?
Yeah, Chroma. Yeah, Chroma. And if you do a search list, say Chroma filters, and they're out in the Northeast. I don't know if it's New York or no, one like it's New Hampshire. They're out of New Hampshire.
Okay.
And they're more expensive, but they are higher quality. I just looked up on my iPhone while I was listening to you guys, and they do show the same thing you showed for astronomics, and it seems like there's less overlap, and they could be twice as expensive. I don't know what Astrodons. We could probably check too.
Yeah. Well, isn't part of the problem also how we define what red is? I mean, is red, 723, I'm making this up, nanometers, or is it a range of 690 to 750? Right? I mean, does one company define it, or does everybody define it the same way? I don't know. I'm just
No.
Yeah, I'm sure their filters, they have filters for all different applications, and one category is astronomy, and they define their red probably with a lot of research from their engineers, but that's just speculation on my part.
Well, mostly in scientific work and spectroscopy and so forth, they create a filter which has a narrow band pass that allows whatever chemical reaction that produces the photon allows to pass through that filter, so you can collect that data. And usually with colors, just another part of the electromagnetic spectrum, there's generally a defined wavelength as a centroid, and then a filters can be made allowing whatever bandpass you want from there, but there's generally a centroid that's defined.
Yeah, and the narrower the filter, the longer the exposure too.
Yes.
Right. But what is that, how do we define what the center is? I
Well,
mean,
normally, for example, with green, I know in microscopy, they'll define it as, I think, 546 nanometers.
right, why isn't it 540 to 550? Right.
Well, probably because somebody had to set, there's
Right.
probably a chemical reaction, maybe chlorophyll or something,
Yeah,
I don't know. It's usually based on some physical phenomenon, like a chemical reaction that determines the wavelength of interest around which filters and things are built.
How about
So-
asking 20 people, look at a color and say, which is red? And let them all pick one, and that's the one you use, the closest one to what they all pick, because we're trying to make it the way we
Well,
see it, right?
Yeah.
So.
No, but it may be fuzzy on, it may be subtle in the narrowest part of the center point. But what you don't expect is you don't expect people to see red when the wavelength coming in is 550. And you don't expect people to see green when the wavelength is 650, right? I mean, most people, 90% of people would agree with that. You're not expecting to see those color confusion issues that far separated. And yet these CMOS chips with these Bayer matrices, they do allow quite a bit of overlap there in a way that we don't really want. We suffer with it, but it's not ideal. And I think Alex is right. The majority of the wavelengths are coming in so close to where you expect the colors to be that we're not achieving a lot of confusion, but there's some confusion in there.
so Alex, maybe you haven't studied this. I'm not looking to give you more work, but is there any advantage from a noise standpoint to collecting L separately or no?
Not, that was part of the point of my talk, was that with modern noise reduction techniques, this 1/square root of n kind of noise reduction, that's by n collecting n subs,
Right.
is not really any better than, and probably not as good as, using one of the noise elimination AI routines, or maybe even other tools that are now available to us, like using the wavelets and suppressing the first order wavelets and things like that. So I think the answer is no, but it's I'm pretty sure the answer is no, and it's because of this evolved technology. And there's most people who have written these noise reduction AI algorithms update them frequently. Obviously, new techniques are coming out for them all the time. So I think that the answer is no now, and it's going to be even more profound no later.
Okay.
I was looking at the prices of those chroma filters, and I think if I buy one, I'll be seeing a lot of red here, but it won't be from the images.
Yeah.
Triggering an
Wait do you
Astrodome.
see the prices of the narrow bands?
Yeah. Well, the IDAS, the one that I'm looking at, the UHS ultra high speed IDAS filter, that looks like a possibility. It's not that expensive. But I understand from talking to the folks at Starzone, it really depends on what you're imaging too. So
Yeah. And I was just, the red, blue, green, I was describing those, and then they had it charted out for looked like very little overlap. Like one of the more experienced imagers could probably take a peek at that. But, like Doug said, it's just a very, this overlap is probably minimal in their real life.
Okay. Well, Alex, as you've stirred up a lot of discussion.
As expected.
Hornet's nest.
All right. We've kind of gone along an hour and a half here tonight, but thank you for presenting that, and be sure to send out a link to the paper again. I think you sent that out once, but if you could send it out again, I'm sure I would appreciate to have that. Our next meeting is on March 20th, next month, the same thing, third Monday of the month. And again, if you have topics that you'd be interested in hearing about, or topics that you'd be interested in presenting, please send those along to me. We're always looking for topics for future meetings. All right, thank you very much. I'm going to stop the recording at this point.
Thanks.
Thanks.
Thanks, everybody.
All right.